All right, so let's look at the enthalpy change of a reaction. And we are specifically interested in, for some reaction, we have a certain amount of reactant, and we're asked to calculate the enthalpy change. Now, the enthalpy change is not the enthalpy change of reaction. That is the pure amount of energy change that is released or absorbed for a specific amount. Remember, the enthalpy change of reaction is sort of like a defined quantity. It's a quantity that we theoretically calculate from the formation enthalpies, or using Hess's law, we get that. And that's not, it's because that this quantity here, the enthalpy change of reaction, is in that kilojoule per mole reaction. Whereas the enthalpy change, which is just delta H naught, is the actual energy change that occurs. In other words, the heat given off or absorbed during the process. So we first want to calculate the enthalpy of reaction and then use that along with the amount of the reagent to then calculate the enthalpy change. Right, so the first thing is to calculate the enthalpy change of reaction. And for that, we use this formula where we use the formation enthalpies and the stoichiometric coefficients of the reaction. So where do we get those values? We get them in a table. So you can look them up on the NIST library as well as in your textbook. So you can look here through these tables. Let's say, for example, so I mean, we're going to work with CO2. So you can find CO2 and you see its formation enthalpy is minus 393.509 kilojoule per mole reaction, kilojoule per mole. So yeah, I mean, that's what we're going to be using. Right, so let's just kick off. So writing this for this reaction that we have. So we first start with the products. So that means it's going to be 4. Now this is a bit of an interesting one because you technically need to write a stoichiometric. So what do we know about stoichiometric coefficients? What are their units? Their units are, then it's 4 mole CO2 per mole reaction, right? And the unit of delta formation H is going to be kilojoule per mole. And this per mole means per mole CO2 per mole oxygen or whatever. So technically what stands here is 4, let me put the bracket here, 4 mole CO2 per mole reaction multiplied by the enthalpy change for CO2, the formation enthalpy, and we just saw that it is minus 393.5. So that's then what you're going to plug in here, minus 393.5, and this one is in kilojoule per mole CO2. Maybe put that in brackets for yourself. So that's like the formal big unit, right, that we're working towards. But I actually just thought of a better way to do this. So maybe let's first just write out it in a general sense. So we're going to say 4 times the formation enthalpy, standard formation enthalpy of CO2 gas. And remember the phases are important. Plus 2 times the formation enthalpy of water, liquid. And from that we subtract 2 times the formation enthalpy of ethylene, so C2H2 gas, and then 50 formation enthalpy of O2 gas. Right, so that's the big thing. So now you just plug in values. So what I just wrote for you are the units. So remember, the stoichiometric coefficients units are technically, you can just write mole per mole reaction. Enthalpies units are then kilojoule per mole. So you see what you're left with. You're going to cancel the moles and you're going to be left with kilojoule per mole reaction. So I'm just going to write the numbers here because otherwise this is going to take literally forever. So we first have 4 times that 4. CO2 is going to be minus 393.5. For water, it is 2 times minus 285.8. And remember, the phases are important. So you have to check for gas, you have to check for liquid, because there's going to be several ones for water and several ones for carbon dioxide. So this is then minus 2 times 226.7 plus 5 times, what you'll notice there isn't one for oxygen. And why? For molecular compounds, so like oxygen, nitrogen, bromine, those kinds of compounds, your formation enthalpy is 0. Okay. For your other compounds then consist of things that are not the same, so not 2 oxygens and 2 bromines just. So CO2 has 2 different components. It has carbon and oxygen. There's numbers. For the other ones, they aren't. Okay, and then what are we left with here? So we said the mole is going to cancel with the mole here. So our unit for the enthalpy eventually is going to be equal to 2599 kilojoule per mole reaction. Okay, but that is what? It's the standard reaction enthalpy. So that's not yet the heat, if you want to put it like that. We need to calculate, or the formal heat for the amount that we're actually burning. So to get to that point, we first need to calculate the number of moles of the ethylene, which is equal to 65.14 gram. So the mass divided by the molar mass, this is 26.04 gram per mole. This will give you a value of 2.501 mole ethylene. All right. Now we can do our unit conversions. You can say that this reaction tells us that there is now delta RH is equal to this minus 2559 kilojoule per mole reaction number. And we know how stoichiometric coefficients work, so it's going to be so many mole reaction for every 2 mole of that thing. Or you can write that cross multiplication. So let's do the cross multiplication one for now. So it is the ratio between C2H2 to the enthalpy of reaction, standard enthalpy of reaction, is we have 2 mole C2H2 per mole reaction occurring. So remember, what are the units of the 2, the 5, the 4, and the 2? They are mole per mole reaction. What are the enthalpies units? Well, we know this corresponds to 2599 kilojoule per mole reaction. All right. We're interested in calculating delta H naught. So not delta RH naught, just delta H naught. And what do we have? We have 2.501 mole C2H2. So what we're technically saying is the formal definition ones contain the mole reaction unit. Now we have a real world situation where we have 2.5 mole of this thing. That's going to give us then a thing that tells us how much heat is released, not how much heat per reaction is released, how much heat is physically being released. So we do our cross multiplication, and you know your units will figure themselves out given that you write them correctly here. So you get on the left hand side, you get minus 2599 kilojoule per mole reaction multiplied by 2 mole, 2.501 mole C2H2 is equal to delta H naught times 2 mole C2H2 per mole reaction All right, so when we divide by the right-hand side, we eventually get, and I'm just going to switch over the sides, so delta H naught is then equal to, let's write it as such, minus 2599 kilojoule per mole reaction divided by 2 mole C2H2 per mole reaction. And this is multiplied by an actual situation where we have 2.501 mole C2H2. Okay, and if you calculate that, you're going to get a value of minus, oh, I don't like that, minus 3250, so 3 significant figures, kilojoule. So it means there is minus 3250 kilojoule being given off during this process if we burn 2.5 mole of it. Right, and I hope you're getting more comfortable with the idea of how to write this conversion part. So meaning this being related to this stoichiometric unit, so that you essentially know you can write by now this is delta RH over your stoichiometric coefficient with its unit multiplied by the actual thing. So if you want to write like a formula for yourself, you'll say it's delta RH naught divided by, we call these units Ni, so divided by N of whatever, so Ni multiplied by NC2H2, whatever you want there. And then that's how it should relate. Where this one's unit, you always just check that it is mole per mole reaction. This one's unit is in kilojoule per mole reaction. And this one is just in mole. And then your units will always work them out. But you know the cross multiplication way, so then you can always just ensure that the units are correct. like that. Okay, and I'll just quickly do the interpretation. What does enthalpy mean? It's a negative quantity here, so it means it's an exothermic process. It's given off 3,250 kilojoules, specifically 2.5 mole of C2H2 gives off 3,250 kilojoules. Okay, that's what we wanted to calculate. We wanted to know how much, if we have so much ethylene, how much energy is going to be given off. And that's the end of that. Okay.